So in today's Learn, Apply, Check video, we're going to have a look at algebraic proof. Before we look at some exam questions, we're going to go through the key techniques and the basics for this topic. So we've got to be able to write algebraically consecutive numbers. We all know that consecutive numbers, if we're writing them just as numbers, would be 1, 2, 3, 4. And they're just numbers which are next to each other in a number line. However, we've got to do that using algebra. So if I pretend that 1 was n, then I know to get to the next one I need to add 1 to it. So my next number would be n plus 1. Then my next number after that would be n plus 2, n plus 3, and so on. For odd and even numbers, well, I know that a lot of you would like to say for even numbers that we would use the letter n, and n must be 2, 4 or 6. However, you cannot say that. It needs to be true for every single value of n. So therefore, an even number has to be 2n. And I'll show you why this is the case. If we used n equals to 1, we would get 2 times 1, which is equal to 2, which is even. If we used n as 2, so an even number this time for n, 2 times 2 is 4, which is again even. So therefore, whatever value of n you use, it will give you an even number. Once you've got what your even number is, it makes it easier to write your odd number, because you know that your odd numbers are exactly 1 away from each of your even numbers. So therefore, odd must be 2n plus 1. So to go from any even number to an odd, you just add 1. Finally, we've got to be able to write consecutive odd and even numbers. So we'll do the even numbers first. So I know if my first one is 2n, then the next one in our number line is 2 away from that first even number. So it'd be 2n plus 2. And then my next one is 2n plus 4. Similarly, for odd, if we start with 2n plus 1, if we think about our number line, our next odd number is exactly 2 away, so it would be 2n plus 3 this time, and 2n plus 5. If you can remember those basics, you'll be able to have a go at every single question on algebraic proof. Question 1. This is your first type of algebraic proof question. They've given you a statement and they want you to prove it's an even number. Well, you'll notice we have got squared brackets here. So what I'm going to do is write that out in full. So 2n plus 1 squared means timesing by itself. I'm now going to expand my brackets. I'm going to get 4n squared plus 2n plus another 2n plus 1, which if I simplify, I'd get 4n squared plus 4n plus 1. I'm now going to rewrite that statement. So instead of writing the 2n plus 1 squared, I'm going to write our answer. And then we want to subtract this entire bracket of 2n plus 1. So now if I subtract these, 4n take away 2n is going to leave me with 2n. Positive 1 subtract positive 1 gives me 0. It wants me to show that it is an even number. Well, just like we showed above, to prove any number is even, if we can take out a factor of 2, because 2 times any number will always give you an even result. So here, to prove it's even, we take out this factor of 2, and then that means we must be left with an even number, because anything multiplied by 2 gives you an even number. So similarly, to prove that something is a multiple of 8, you would take out a factor of 8. So now's your chance to pause the video if you would like to have a go at this question before I solve it. So in this question, again, we've got 2 pairs of double brackets. So my first job is to expand them separately. So now I've expanded them separately, it wants us to subtract them. You'll see I've lined them on top of each other, so therefore I can clearly see that I need to do 4n squared subtract 4n squared, which gives me 0. Next I need to do 12n subtract negative 12n. So we've got positive 12n subtract negative 12n. This gives me positive 24n, because we remember two negatives next to each other give you a positive. And our final step, we've got positive 9 subtract positive 9, which again gives you 0. So we have a final answer of 24n. To prove something's a multiple of 8, well, we know for it to be in the 8 times table, it must be 8 times something. So if we take out that factor of 8, we will then have shown that it must be a multiple of 8. Just conclude that at the end, therefore a multiple of 8. So our next type of algebraic proof question is a statement which looks like so. So this is where we need to remember those basics from above. So to write two consecutive even numbers, we remember that the first even number would be 2n, and then the next even number is exactly 2 away from that. So we'd need to add 2 to that first term. Then we read it. So it says that we need to prove that the sum of the squares of the two consecutive even numbers is always a multiple of 4. So now we need to square both of our terms. And remember, write it out as double brackets if necessary. This will mean that you don't expand it incorrectly. So we get 4n squared plus 4n plus another 4n plus 4. And if we do 2n times by 2n, you get 4n squared. If we now simplify this first one, we get 4n squared plus 8n plus 4. And it wants us to sum up our answers. So that means we need to add together both of our answers. So 4n squared plus 8n plus 4 plus this 4n squared. That gives a total of 8n squared plus 8n plus 4. We wanted to prove it was a multiple of 4, therefore we take out this factor of 4. That leaves us with 2n squared plus 2n plus 1. Therefore, it is a multiple of 4, as we've took out the factor of 4. So if you'd like to pause the video now, you can, and have a go at this question by yourself before I go through it. So here in question 4, again we'll read it. It wants the difference between the squares of any two consecutive odd numbers this time, and proving that it's a multiple of 8. So to begin with, let's write down two consecutive odd numbers. So my first one would be 2n plus 1, and my second one 2n plus 3. I now need to square both of these. So you'll notice that I've written the larger one on top, because this will make it easier when we subtract them. So 4n squared take away 4n squared is 0n squared. 12n take away 4n is positive 8n. 9 subtract positive 1 is 8. It wants us to show it's a multiple of 8, therefore we need to take 8 outside of the bracket and factorise. Then we write our concluding statement that therefore it must be a multiple of 8. So question 5, our last type of algebraic proof question, and it's given you a statement and it wants you to show that it's never an odd number. So to begin with, we need to have a look at that statement, and we are going to factorise our n squared minus n. So we're going to take out the highest common factor, which in this case is n by itself. That leaves us with n minus 1 in the bracket. We have two scenarios now. if n was odd, that means n minus 1 must be even, because if you take 1 off an odd number, you'll get an even number. That means we're going to do an odd number times by an even number, which we know is always even. That is our first case scenario. However, we also have n could be an even number. Well, if we start with an even number and subtract 1, that means we must have an odd number, and we know any even number times any odd number must also be even. So therefore, we have just shown whatever you start with must always be an even solution, and therefore never odd. So our final question, if you'd like to pause the video to have a go at it before I go through it, pause it now. So here it tells you to prove algebraically the difference between the squares of two consecutive integers is equal to the sum of the two integers. So first of all, we need to write down two consecutive integers. So we could choose n and n plus 1, because they would be next to each other in the number line. We then need to square both of them, so n plus 1 squared, which is n plus 1 times n plus 1, which is n squared plus 1n plus another 1n plus 1, and n squared is just n squared. If we simplify our first one, we get n squared plus 2n plus 1. It wants to know the difference between these, so we're going to subtract them from each other. That will leave us with 2n plus 1, because our n squareds cancel each other out. Then it says we need to show that it's equal to the sum of these two integers. Well, the sum of n and n plus 1 is 2n plus 1, so therefore we have just shown that yes, they are equal, as both answers are equal to 2n plus 1. So we can summarise that at the end. 2n plus 1 is equal to 2n plus 1.